If an engineer lacks sufficient experience in design analysis, they tend to focus on fault detection. Within the engineering community, there is a tendency to prioritize calibrated tools for evaluating air handling units' performance, sometimes overlooking the crucial aspect of design analysis. Relying solely on trust in the design is not always the optimal approach. I emphasize this viewpoint based on my extensive 38 years of industry experience, during which I identified numerous design errors in AHus from reputable companies. In this context, our evaluation process involved measuring air properties before and after the heat exchanger, as well as monitoring glycol flow and return temperatures. This approach allows us to acquire a comprehensive understanding of the AHus performance. Notably, we observed the glycol valve being fully open during these evaluations. Our objective is to accurately assess the cooling heat exchanger's capacity under optimal systems condition. Prior to conducting fault evaluation, it is imperative for engineers to meticulously scrutinize duly validated documents, commissioning reports, and design specifications. In the event of unavailability or absence of requisite documents, the engineer must undertake comprehensive system analysis to effectively proceed with the evaluation process. In this case, the engineering team is currently conducting an in-depth investigation into potential fault associated with elevated glycol flow temperature. It is essential to clarify that attributing a fault directly to the air handling unit might not be accurate, especially when the glycol is sourced from a third party. The issue could lie within the chiller system, impacting the AHU heat exchanger functionality. It is rely on chiller water temperature to effectively cool the air that passes by. In instances where the temperature control system exhibits anomalies, pinpointing the root cause can be challenging, particularly if the design or control system is suboptimal. A poorly designed system might not provide detailed insights into the specific reason for the temperature control failure. Instead, it might present a generalized problem of elevated temperature within the premises, leading to confusion amongst engineers tasked with managing the AHU. This lack of precise information can result in frustration and hinder the troubleshooting process. Clarifying these potential complexities and nuances is crucial for an accurate and efficient resolution of the issue at hand. Unlike in the other situation, this scenario appeared to indicate a potential fault related to the AHU system. If the fresh air intake temperature and the air volume are within the AHU's maximum air processing capacity, further investigation is warranted. Particularly attention should be given to instances where temperature differential in the glycol flow and return remains high despite the glycol valve being fully open. In such circumstances, it's advisable for the AHU engineer to liaise with chiller engineer responsible for glycol flow. A formal request for a comprehensive report regarding the integrity of the mainstream glycol flow should be made to ensure a thorough examination. Should the glycol mainstream flow be confirmed as sufficient by the chiller engineer, the AHU engineer should proceed with meticulous examination of the local strainer, glycol valves, and heat exchangers for any indication of blockages or other impediments. The glycol temperature differential between the flow and return can be influenced by the increased air volume passing through the heat exchanger. In certain instances, driven by financial constraint and desire to enhance production, some systems are subject to incorrect modification and are left inadequately conditioned. This scenario is visually evident in the provided image, where the air volume surpasses the air handling unit processing capacity. Consequently, the air remains uncooled, failing to attain the desired set point temperature. This leads to an escalation in the glycol temperature differential. If the engineer overseeing the system does not cross-reference the AHU specification, they may erroneously pursue investigation in a potential glycol circulation issue. It is essential for engineers to carefully analyze and ensure that the system modification align with the equipment specification to prevent misdiagnosis and optimize performance. The current scenario pertains to user system requirement specification. It is evident from the provided information that the AHU it is inadequately designed to withstand outdoor temperatures condition. The air handling unit is unable to effectively process the incoming outdoor air at elevated temperatures, thus failing to attain the desired set point. A critical aspect in this situation it is the adherence to AHU's design specification. It has been observed that many engineers might not thoroughly review the AHU specification, which ultimately result in their inability to address this issue effectively. Consequently, they face scrutiny for their perceived incapacity to manage the situation adequately. Emphasizing the significance of AHU specification document is paramount, especially regarding potential modification to the AHU. Any unauthorized or incorrect alteration made to the AHU demand immediate attention and remediation by specialized professionals to optimize the system alignment with the original design specification. In the context discussed, the air handling units designed to exclusively intake fresh air and avoid air recirculation require meticulously calculated heat exchangers to precisely regulate airflow temperature and humidity. While the video might portray an appearance of perfection, I will elaborate on the control philosophies of a site that leads to temperature and humidity fluctuation within the clean rooms. Watching this video, it becomes evident that the heat exchanger's capacity is regulated by a combination of factors such as glycol temperature and glycol flow. These factors are managed through valves which are progressively adjusted by actuators following instructions from PLCs, programmable logic controllers. Up to this point, the control mechanism appears sound. However, a critical error lies in the control philosophy's design, specifically concerning the placement of temperature and humidity probe. The temperature and humidity probe is positioned within the extractor fan duct. This configuration causes a delay in capturing changes in air temperature and humidity. Consequently, the PLC receives instructions from the probe situated into the extractor's fan duct, resulting in delay responses by the actuator. This delay manifests in the temperature and humidity trends as illustrated below. Regrettably, this delay in response can cause temperature and humidity within the clean room to deviate from the desired parameters. Many engineers might begin to focus on identifying faults rather than evaluating the fundamental design. Insufficient understanding of the system can induce significant stress among engineers and attract scrutiny from the management. It is essential to address this control philosophy error to optimize the performance of the AHU and ensure a control environment within the clean rooms.